Hi, welcome to the ninth video on Introduction to Physics for Neural Network. In this video, we shall see how to solve Euler equation using PINNs. So Euler equation is quite fascinating equation because it does not have any viscosity and is one of the governing equation in supersonic flows. So here this U is conservative variable, F is flux variable and G is also a flux variable. So this is a general form of Euler equation. So one of the beauty of Euler equation is that will produce shocks with zero thickness. That means we'll be having shock like this. So most of our mathematical models directly calculate the derivatives. Even if we use the integral or peak formulation, in some sense, we have to calculate the derivative across the shocks. So whenever we calculate the derivative across the shocks, especially when we have step-like function, it's supposed to give you a infinite value. But we know we cannot deal with infinite value. So what we do is we will try to smoothen the shocks a little bit by adding some viscosity. Euler equation. So this is the viscous part. It looks like a Navier-Stokes equation, but this term is not explicitly same as the Navier-Stokes equation. But for incompressible viscous part, these are more or less same. So the moment we add some viscosity to this Euler equation, the shocks will spread over several grid points. So moment the shock become little bit smoother, this will not give an infinite derivative value. So this is the principle behind all the numerical schemes as well as spins. So that we already discussed in the Burgers equation. So now our problem is if we add too much viscosity, more mu value, big mu value, that will smear the shock structure. But if we give a very small value, that will destabilize the solver. So we have to find the optimal mu for the shock. So that's $1 million question in high-speed flows. So here we have shown the adaptive viscosity architecture. This is a slightly modified version of the traditional PINN architecture. The only difference is the solver itself learned the optimal mu. So here we give xy as the xyt as the input of the PINN. So we know for Euler equation these are the variables we are interested in. In addition to that, it will also write mu. So mu will become a space-time quantity. So that's the beauty of this equation. This is first introduced in PINNs by Coutinho in this paper. So this is one of the beautiful concepts. Already told in traditional CFD methods, we define this mu through some algorithm. For example, GST scheme has its own way of defining mu. Likewise, all these schemes has its own way of defining the mu. So how they come up with this, they test on several problems and give that mu. But in PINN, it can learn the mu based on the problem requirement. That's the uniqueness of the PINN. In addition to that, we know the moment we give some free parameter to the mu, it will try to make the problem as smooth as possible so that the solver won't destabilize. So what we have to do is we should add an extra constraint. So because we are solving Euler equation, we should ensure the mu is minimized to 0. Otherwise, we will get a very smooth shocks. So this you can visualize the penalty term or regularization terms. So we know we are calculating derivative of the shocks. So across that shock, the residue value will be very high. Even if we have very sharp structure, this will be very high. So this loss will be very big value. So what we have to do here, we should reduce the weight to stabilize the solver across the shocks. But if you don't give too much weight, solution won't propagate. So we should find an optimal way that should ensure the propagation of the solution as well as the solver shouldn't blow up. So that's why we use the adaptive weight. Here weight will change based on some parameter. Usually it could be based on gradient. But one of the beauty of physics informed neural network paper by Liu et al. They have proposed a new weight. So this weight can be able to give a better shock resolution than any shock capturing schemes I know. So this weight was introduced by the great von Neumann in 1950s. So Liu et al. Adapted this weight in PINNs and they produced the best result. So they didn't introduce adaptive viscosity, they used the adaptive weight. So moment we don't include adaptive viscosity, sometimes we may miss some of the flow features. So here you can notice that we miss the contact discontinuity. So another important problem is moment we go for adaptive weight, we have to give more weightage to the initial condition than the PDE. So that will also reduce the propagation of the solution. So in order to cure this solution, we come up with another procedure, that's the adaptive weight viscosity concepts. You can, maybe if you are interested, you may refer about paper. So here we are adapting both viscosity and weight to achieve a better solution. So in this problem, we will be using adaptive weight viscosity solver. So this is a short shock 2 problem. We already saw that's based on Euler equation. The initial condition that we have used is this one. So this is the famous experimental setup. So if you want to visualize a supersonic flows, we use a shock tubes. So that's a beauty of this problem. This also has small application. So this is a solution contour of density. And this is a solution animation over time using paints. So you can notice how crispy these shocks are. Here we have used only 101 grip points on the spatial location and 101 grip points in temporal locations. So here we have compared our solution with the muscles, pins, and we know this is we know OA is our that we introduced in 2023. So this is one of the best schemes I know, and we have also shown it for some test cases it can save a computer's cost 6 to 7 times compared to the traditional schemes. So even if you compare the best scheme, PINN is much better than the schemes or muscle schemes on a given grid points. But if you take a given error or given error, uh, traditional methods will outperform the PINNs. So this is RMS error on the given grid points, so that you can notice that PINN is less erroneous when compared to other schemes, other as well as higher order schemes. So for all the problems what we have tested can be generated using Gemini. You can also test Claude. Claude is producing even better code than Gem supported papers. But this problem they are unable to solve. When I asked several prompts, but it was unable to give the better code. Anyways, giving some result, but results are not even closer to the exact solution. So this is a domain setup and number of viewpoints in space and other stuff. I hope you are very familiar with this because we already saw this thing for the last few demos. So this is the initial condition for the short tube problem. So here we already introduced also we have used the parametric turn h. So we already used this parametric turn h in one of our test cases. I think we have used it for heat equations. So only difference is for this activation function will be like kx. So k is a tunable parameter, but in turn h. But in traditional turn h, it will be like a turn h x. So that's the difference between the standard turn h and this parametric turn h. Here, the neural network learns the optimal k, so that it can produce that this curve, because turn h curve looks similar to this. But if we have a high k value, that will become like a shock end of structures. If the k value is very small, that will become like this. So this may be relatively more helpful when we solve problem having shocks. And this is a neural network configuration that we have used. We just used 15 neurons and we have used 5 layers. And this is a PDE loss. So here the neural network will write 4 output, that is rho, P, U and viscosity. So these are the Euler equation. These are the residues of Euler equation. Here we also have one extra other objective function, that is mu square, that we are minimizing to 0. And this is the initial condition loss. In PyTorch, we have to specify the device, whether it's a CUDA or CPU, but in TensorFlow, it's not required. So this is a collocation point that we have defined over the domain and the initial condition over the domain. You can also use latent hypercube sampling. That may reduce the number of breakpoints, but I prefer uniform breakpoints. So you can also try adaptive collocation grids or adaptive grids. That will also reduce the computational cost. So this is a closure equation. So this is the loss function, and we are calculating gradient of the loss here. So here we are initially using Adam's optimizer. Then we are refine the result using LBFGS optimizer. So when we do this, we will be getting results like this. So you can notice that it can able to resolve the shocks on almost 2 breakpoints. Probably you can even tune it better. You may able to resolve when contact discontinuity even better. So I hope you have enjoyed today's video. In the next video, we shall see how to solve a supersonic flow over a wedge using pins. So thank you for watching.